All right, welcome back. So in the last lecture, we defined the complex logarithm as the inverse of the complex exponential, and we found something a little bit surprising, which is that the complex logarithm of a number z, a complex number z, actually has infinitely many values. There's not just one logarithm of z, there's a whole infinitude or infinitely many values that are equally valid for the logarithm of z. So in this lecture, what I'm going to do is I'm just going to give a really quick recap of why that's true. I think that the last lecture, the first time anyone hears about the complex logarithm, it's a little confusing. So I'm going to just really simply give a recap, but we're going to use it specifically to answer questions about things like how do you compute, the nth root of 1 or the third root of I, or more generally, what are these equal to? Or more generally, if I have some, z to the 1/4 power equals 1, what values of z will satisfy that equation? Okay, so this is kind of the topic of today. And the way I'll write this mathematically is we're going to be looking at functions. Again, we're talking about functions of a complex variable. We're talking about functions z to the power a, where a is no longer an integer. We know how to take z squared, z cubed, z to the 4th power, and so on. How do I take z to the 1/3 power, or z to the 1/n power, or z to the πth power? How do I do things like that? And we're going to use the complex logarithm to do it. So maybe the first thing I'll do is I'll tell you how we're going to analyze these functions, because it's going to allow us to do things like compute the n roots of 1 or the 3 roots of I. We already know that the square root of a number, there are 2 square roots. The square root of 9 could be +3 or -3. The square root of -1 could be +I or -I. Similarly, there are 3 cubed roots of any complex number. There are nth roots of any complex number z, and we're going to figure out how using this complex logarithm formula. So the first thing we're going to do is we're going to rewrite this z to the a using exponentials and logarithms. So we're going to rewrite, essentially, this may be rewritten using exp, the exponential function, and log, the logarithmic function. And specifically, the way we're going to do that is we're going to say that z, sorry, let me think. So z is going to equal e to the log of z. Log of z is infinite valued, but e to that only has one value. That's the way I'm going to explain this again in a way that's less confusing. So this is definitely true because log and exponential are inverse functions. If I take the log of z, all of these values, but then I exponentiate any one of them, I recover z. So this is definitely true. And so we're going to essentially use that to show that z to the power a is equal to e to the, it's this to the power a, which we also know is e to the a log of z. So we're going to take this expression for log of z, we're going to multiply it by that power a, so a log of this plus I a times that, and we're going to see what falls out when we take the exponential of that. And that's how we're going to define functions like z to the 1/2, or z to the 1/3, or z to the -1/3, things like that. Okay? Now, before we get into this, and before we solve for, the square root of I, or the third root of I, or things like that, I'm just going to very quickly recap why this logarithm was infinitely valued, and why that's not actually that confusing at all, okay? So specifically, we wanted, if we think about z in the complex plane, so z is this number in the complex plane, and it has a radius, and it has a principal angle between 0 and 2 pi, just the way we always define angles between 0 and 2 pi. If I add another 2 pi to that theta, it's exactly the same point. So plus 2 pi n is exactly the same point as long as n is an integer. So when we say n is an element of the integers, this is just a math way of saying n is an integer, then this z could be defined using any of those angles. Let's say this was 30 degrees. 30 degrees is fine. So is 390 degrees. So if this was pi sixths, then pi sixths plus 2 pi is also valid. Plus 4 pi is also a valid way of defining z. We normally only choose the principal value between 0 and 2 pi, but I could add 2 pi to that any way I like. And the real catch here, I think what was confusing last time for me, I confused myself, is that if I add 2 pi n to that phase angle, this value z doesn't change. It's not like there's infinitely many z's. Z is x plus iy. There is a single real value x and a single real value y that uniquely defines that complex variable z. But in the phase angle way of writing it, there are infinitely many thetas that are equally valid for getting that real x and that real y. I could use the principal theta, theta pi, or I could add 2 pi, add 4 pi, add 6 pi. Just because there's different ways of writing it in the complex plane doesn't mean there are infinitely many z's. There's just z. It's a complex number. It's a real thing that exists, and it has there's one value z. But when I compute the logarithm, specifically so that the logarithm is the inverse of the exponential function, now all of those many ways of writing that phase angle in terms of adding multiples of 2 pi are all valid for this complex logarithm. Because the logarithm of z is specifically log of the magnitude of z. Sometimes we call this the radius. This is just r, plus I times any angle that if I took e to this angle, it would recover z. And now all of these infinitely many angles are all valid, because if I took e to this number for any integer n, I would recover z. Now, even though there was only one z in the first place, there really are infinitely many log of z's. This is u plus I v. And these actually are different v's. It's not like here where just going around I get to the same place, the same exact z value. Here, if I add 2n pi, I have a new v. V is actually 2 pi n bigger. So there's this number w equals actually changes when I rotate around, and I add 2 pi to this phase angle of z. So I think that's where it gets really interesting to me, is that this input variable z is uniquely defined. It has one value. This is one value. But the logarithm, there are many values for this v that when I took e to that u plus iv, I would recover z. And these are actually different values v in that complex logarithm. The way we drew it before was, this is the z plane. The w's that are valid are all on this line real w equals log of the radius. But then I have many values for this v term, for this phase angle here, that are all valid. So there's the principal theta, but then plus 2 pi, plus 4 pi, plus 6 pi, 8 pi, 10 pi, minus 2 pi, and so on and so forth. So I just wanted to clear up. It's not that weird that this complex logarithm is multi-valued. It's a property of the fact that there are many ways of writing this phase angle. I could add 2 pi I as many times as I like to this phase angle, and this value of z doesn't change, but those are all valid logarithms of z. Good. So we're going to use that property that this is infinite value, that this is true for any integer n, to define, what is the cubed root of z, what is the square root of z, the fourth root, and so on and so forth, the nth root of z. So we're gonna, for example, this could be, for example, e.g., for example, z to the 1/2 is the square root of z. So, you know, if a was 1/2, I'd be computing the square root of z, things like that. So I want to define what these functions are. We know what z to an integer is. What is z to a fraction, like 1/2 or 2/3 or something like that? Okay, good. And this is the basic formula we're going to use to define that quantity. Now, before I actually take this logarithm and plug it into this formula, I want to give you an example. I want to give you an example of what is the cubed root of 1. Okay, because I think this is something that everybody's going to understand, and it's a pretty simple concept. So I'm going to draw my, how do I want to do this? I'm going to draw my complex plane. And I'm going to draw so here's the problem we're going to solve. We're going to say cubed root of 1 equals what? Okay, so that's another way of saying, you know, z to the 1/3 is our function, and z equals 1. So we're trying to understand the function z to the 1/3 power, and we're evaluating that at z equals 1. What are the values that are valid for z to the 1/3? Now, we kind of know already that one of the cubed roots of 1 is 1, because 1 to the cubed, you know, to the 3rd power is 1. So I know that 1 of the cubed roots of 1 is going to equal 1. And I'm going to call that e to the 0. We know that 1 equals e to the 0. That's just saying radius equals 1, theta equals 0. This is e to the whatever I0, if you like, e to the 0. But what's interesting is that if I took, how do I want to write this? Let's say that this number, the cubed root of 1, let's call that, you know, let's call that q, just to be cute. So we're saying q cubed equals 1. And so I know that e to the 0 is one solution, e to the I0, but I'm going to claim that 2 pi n, I can add 2 pi n to that, and that's also going to equal 1 when I cube it. So let me show you. I'm going to draw the picture, then we're going to derive this. I think this will make it easier to understand. So if I'm just going to draw the answer because I think I want to show you and then explain. These are the other 2 cubed roots of 1. There are 3 numbers that if I cube them, I will get 1, which means specifically this angle here, this theta, so this e to the 0, this is the principal cubed root of 1. But if I take, you know, 2 pi divided by 3 and add that to the phase angle, that's another cubed root of 1. Still radius 1, but now this is the phase angle. If I take a number, you know, q equals e to the I 2 pi thirds, and I cube it, q cubed is e to the I 2 pi thirds times 3 is 2 pi. And what's e to the I 2 pi? Well, it's e to the 0. I got back to where I started. So if I take this wedge times 3, I get back to where I started. So this is also a cubed root of 1. And then similarly, this one here, which is 4 pi thirds, is also a cubed root. Let's call this, you know, this is the second one. The third one is e to the I 4 pi thirds. Again, if I take this number and I take it to the 3rd power, q3 cubed, I get e to the I 4 pi, which again, what is e to the I 4 pi? It's e to the 0, because if I go around 2 pi twice, I'm right back where I started. And so you can kind of imagine if I take this angle, 4 pi thirds, and this is, you know, this is q squared would get me here, and q cubed would get me back to a phase angle of 0. So these are all totally valid cubed roots of 1. I can have e to the 0, e to the, let's write this very, very explicitly, e to the I 2 pi thirds, that's this point. This is e to the I 4 pi thirds. Now you might think, well, why isn't there a fourth cubed root of 1? Why can't I do this again? And the reason I can't do it again is because, I'll write it in red because it's an invalid solution. If I said q equals e to the I, let's try to do 6 pi thirds. Well, what is e to the I 6 pi thirds? That's just e to the I 2 pi, which is e to the 0. So e to the 0 is e to the I 6 pi thirds. And so once I go around again, and I can't do 8 pi, because this is also e to the I 8 pi thirds, and this is e to the I 10 pi thirds, e to the I 12 pi thirds, e to the I 14 pi thirds, 16 pi thirds, 18 pi thirds, and so on and so forth. So even though I can keep adding 2 pi over and over and over, eventually those cubed roots start to be the same thing. They all mean the same thing. There's only 3 unique cubed roots of 1. Okay, so I'm going to derive the general formula, and then we're going to revisit this again. So this is actually really fun and I think kind of illustrative to start just playing around. Just like pick some complex number, I, and compute all of its 4th roots. Pick a complex number, 1 plus I, and compute all of its 9th roots or its 4th roots or whatever. It's very, very helpful to understand what's happening here. Okay, so I want to just, we're going to revisit this, but the basic idea is that the cubed root of 1, there are 3 values because there are 3 unique phase angles that if I cube them, I'll get all the way back to e to the 0, or e to the 2 pi or e to the 4 pi. And there are only 3 unique values because if I keep doing that trick, I basically reinvent these 3 solutions that I've already discovered. There's only 3 unique solutions. Why don't we do the same thing for -1? Let's just do this again just to make sure we understand. So let's try, what is the cubed root of -1? We should be able to do the cubed root of -1, the cubed root of I, anything we want. So again, okay, -1 is one of the principal cubed roots of -1 because -1 times -1 times -1 equals -1. So this is already one of the cubed roots. And this is e to the I pi, right? I've gone pi to get here. And this is what we call the principal cubed root of -1. And again, what I'm going to do is I'm going to take 2 pi thirds and I'm going to add 2 pi thirds to this. So 2 pi thirds gets me here. And I'm going to add 4 pi thirds, which gets me here. And if I added 6 pi thirds, I'd rediscover this point again. If I added 8 pi thirds, 10 pi thirds, 12 pi thirds. So there's only 3 unique versions of this. This is e to the I pi plus 2 pi thirds. This is e to the I pi plus 4 pi thirds. And again, this is, also equal to e to the I pi plus 6 pi thirds, and so on. So these are kind of, it repeats at some point. And these are the unique cubed roots of -1. You can easily verify that if I took this number and I cube it, right, let's just take this number cubed, this cubed equals e to the I 3 pi plus 4 pi, which is equal to e to the I 7 pi. But if I go around, 7 pi times, it's the same as just going around e to the I pi. So this to the 3rd power gets me where I want to go. Similarly, this to the 3rd power, it'll go around, I think instead of 7, it'll be 3 plus 8 is 11. It'll go around, and get me to e to the I pi. So these are the principal cubed roots. It's really easy to verify. Once you've found one of these, it's really easy to verify. You just take the cube of that and see if it's the number you want. Okay, good. So now I'm going to derive a generic formula for this, which is, and then maybe I'll do, the cube root of I, just because it's really useful to see one of those cases as well. So the idea here is we're going to use this expression, and then we're going to show that out of all of these infinitely many values of log, only some of them are unique when I'm taking z to the power a. Okay, maybe I'll use yellow here. So let's, as kind of a general example, let's take a rational a. And by a rational a, I literally mean it's the ratio of two integers. So this equals m over n. We say that this is an element of the set of rationals. That's just what in the set of rationals means, which is a subset of real numbers like pi and e and 3 and -2. And what we mean is that m and n are both integers. So this is the ratio of two integers. This is just the mathy way of saying it. Then what we're going to say is that z to the power m over n equals e to the m over n log of z. And I'm going to use this whole expression here and plug it in. And so that's going to mean I have e to the m over n log of radius plus I m over n times my theta principal plus any 2 pi, sorry, this is a different n here, we'll use k, times any integer times 2 pi. Right, so this is just m over n times the logarithm of z, okay? And I'm going to break this up into the real part, the magnitude part, and the cosine and sine part. And so this equals e to the m over n log of r. This is only one value. There's only one value here. So I was taking the third root of 1. If I took the third root of 8, then I would have to take the third, then the radius of that would be the third root of 8. Okay, so if I took the third root of 8, that would be, the magnitude of that would be the third root of the magnitude of 8, so that would be 2, or 2 times e to the I 2 pi thirds, or 2e to the I 4 pi thirds. So this is just the magnitude part. If I didn't, if I had something that was non-trivial magnitude like length 8 instead of length 1, I'd have to take the third root of that length as well. Okay, so there's that, times e to the I. I'm going to break this up. I'm going to say this is e to the I m over n theta p times e to the I m over n 2 pi k. Okay, that's all I've done is I've just taken z to the m over n, I've used this formula for it, and I plugged in the complex logarithm, and I've gotten these. Now, this term is single valued, and this term is single valued. This term is true for any integer k, k1, k2, k3, k0, and so forth. And so now what we're trying to do is we're trying to find, there are only so many unique values of this quantity before it starts repeating on itself, which is what we saw here. So, for example, if if m over n equals 1/3, then this would be equal to e to the 1/3 log of r, which is the same as r to the 1/3. This would be e to the I theta p over 3. And this would be e to the I 2 pi k over 3. And what I claim is that there are 3 unique values of k where this is unique. So let's try k equals 0. Then this is e to the I 0. That's fine. K equals 1. That would be e to the I 2 pi thirds. That's one of my principal cubed roots of 1. That's fine. This is different than e to the 0. These are different numbers. K equals 2 would be e to the I 4 pi over 3. Again, that is a different number than either of these two. This is an actual different complex number than these guys, okay? But when I go to k equals 3, I come back to where I started. If k equals 3 here, I have e to the I 6 pi thirds, which is e to the 2 pi I, which is the same as e to the 0. E to the 2 pi is e to the 0. This is the same as k equals 0. And I'll just show you, k equals 4 is e to the, goodness gracious, 8 pi thirds, I 8 pi thirds, which again is the same as e to the I 2 pi thirds. These are the same number. It's just, you've gone all the way around. And so what this means is that there are only 3 unique values of k where these numbers are actually different. K equals 0, k equals 1, and k equals 2. And for all of the other k's, you've essentially just gone around and re-found this number, or re-found this number, or re-found this number, and over again. So I think that's really, really interesting. That kind of shows why. And if this was 1/4, there would be 4 unique numbers before you get back to where you started. If this was 1/5, there would be 5 unique numbers before you get back to where you started. And that's why there are 3 unique cube roots of a complex number. There are 4 unique 4th roots of a complex number, and so on and so forth. Okay, it's literally because this complex logarithm, when you divide, when you multiply it by this rational number, there are exactly n unique values of k that give you different numbers for this quantity here, after which it starts recycling back on itself. Okay, I think that's super duper useful. And this means I can take the 4th root of I can take the 9th root of 1 plus I can take any complex number I like. And if I write it in polar form with a principal angle, and I use this formula for the logarithm, I can find every single nth root of this complex number. I can take z to the 1nth or the 2nth or 3nth or whatever, and I can find all n unique roots of that number. Sometimes these are called, there's a saying in complex numbers called the roots of unity, the 3rd root of 1, the 4th root of 1, the 5th root of 1, because they form these kind of canonical pictures that you can use to compute other roots of other numbers. Good. This actually begs the question. There's some really weird stuff that happens if you take z to the a rational number. If I take, if I take z to the pith power, this is an irrational number. There is not an integer m and n that I can write pi in terms of. And so if I take -1 to the pith power, there are infinitely many, this is super weird, there are infinitely many values of -1 to the pith power. Because for every single k, for every single n here, for every single k here, if I plug in a pi here, there are infinitely many values of this. And in fact, I would say that any number here on the unit circle is a solution of -1 to the pi power. That's a very weird and strange outcome of the fact that log of z is infinite valued and pi is irrational. It's a weird thing, but it's true. Good. What else do I want to say? Maybe I'll just do a couple more examples because I think this is really helpful. Let's see. Okay, I'm just going to erase this because I actually like this formula better. Let's do the 4th root of I, and then we'll call it quits. Okay, so if I take, sorry for the squeaky pen. So let's say I have, or let's take, the 4th root of 16i, because I want to show you what happens if you have a if it's not length 1. So in this case, well, let's write 16i is equal to 16 e to the I pi halves, okay? So the number I is just e to the I pi halves, because it's in the pi halves angle. And 16I has a radius of 16. So this is the radius, and this is, e to the I theta principal. Theta principal is pi halves. And so if I want to take the fourth root of 16I, I basically take, r to the 1/4, and then e to the I theta p to the 1/4 times e to the I 2 pi k fourths for all integer k until it recycles on itself. Okay, so the radius to the 1/4 equals 2. I chose 16 because its fourth root is 2. So the magnitude of all of these fourth roots, they're going to have radius 2. This is e to the I pi eighths, okay, because that's what the principal angle divided by 8 is. And this is really easy to understand. If I took this, this is, let's say this is 16I, then the first principal fourth root of this is going to have, I'm going to divide this into 4 pieces. So it's going to have length 2, e to the I pi eighths. Because if I took this to the 4th power, I would get 2 to the 4th is 16, and e to the pi eighths to the 4th power is e to the I pi halves, which is this thing. This is 16 e to the I pi halves. So this is my first principal fourth root of 16I. But now I also have this plus 2 pi fourths plus 4 pi fourths plus 6 pi fourths, and so on and so forth. So e to the I, and I'm just going to say 2 pi fourths is pi halves k. And I'm going to choose k until this thing recycles on itself. So k equals 0, k equals 1, k equals 3. Can't count. This has been a long day. K equals 3 and k equals 4. So at k equals 0, I just have 2 e to the I pi eighths. That's this solution here. For k equals 1, I have 2 e to the I pi eighths plus I pi halves. So that's I 5 pi eighths. For k equals 2, and 5 pi eighths is just this plus pi halves, which is a little hard for me to draw, but it's something like that. If I have k equals 2, then this is 2e to the I pi eighths plus pi, which is, goodness, that's going to be I 9 pi eighths. I'll do k equals 3 is 2e to the I probably 13 pi eighths. And by the time I get to k equals 4, I'm going to get 2e to the I, add 4 again, I'm going to get 17 pi eighths, which equals e to the I pi eighths. So by the time I get to the 4th k, and the 5th and the 6th and the 7th and the 8th here, I essentially have rediscovered the same numbers that I was using originally. So for k equals 0, that's this one. For k equals 1, it's this one. K equals 2, each of these I'm just adding pi halves. I'm just rotating by 90 degrees. This is just 90 degrees or pi halves. So the next one is going to be here, and the last one is going to be here. And what's really cool is that all of these nth roots of any number kind of form this star pattern where they all are equal distant to each other, dividing 360 degrees. So these, were each 120 degrees separate, or 2 pi thirds separate. Each of these are 90 degrees, or pi halves separate. And at some point, there are only 4 unique fourth roots of this number, because after the 4th unique one, the next one, I'm basically back where I started. And if this was the 5th, nth root, I would get a star pattern with 5, like a pentagon. I would get things equal spaced 5 ways. If I took the 6th root, I would get things equal spaced 6 ways, and so on and so forth. So it's really cool. There's this kind of geometric picture, but this is all related to the fact that the complex logarithm is infinite valued, and so you can use that when you're computing z to a fractional power, like the square root of I or the cubed root of -1 or whatever you like. Okay, I would recommend practicing this, try this out. You can basically do this for any number z. You can try this out and you can figure out where this thing recycles. Okay, thank you.